Hey folks, so welcome back to another lesson. This is going to be on the topic of waves, and we're going to focus on travelling waves today, and in particular look at the definition of a wave. Going to recap some basic concepts of waves from higher, use the term phase to describe waves, describe how energy is transferred by a wave, and state the equation of a travelling wave, and carry out calculations using these equations. Now, this last bullet point here will focus that on the second lesson. So to start off with, what are the basic characteristics of a wave? And you might think you don't know a lot, but you have done a lot in Nat 5 and higher as well. And in particular, even in advanced higher, we have looked at the mathematical descriptions of what a wave is. So pause the video and try and write down as many things as you can. Hopefully you gave me a whole bunch of things like a crest, a trough, an amplitude, a frequency, the speed of a wave. You might have remembered from our simple harmonic motion that the simple harmonic motion is described by y is equal to a sine omega t, which when you sketch it looks like a sine wave, or y is equal to a cos omega t, which is the other solution depending on the initial conditions of the actual harmonic oscillator. So you know a heck of a lot of stuff about waves, so we're going to build upon some of those ideas in advance higher. So first of all, what is a wave? Well, a wave can be described very generally as a disturbance in a medium which moves from one place to another. No net mass is transferred and only energy is transferred. So you've come across things moving through a medium. So for example, sound waves, which move through water or air. You could have electromagnetic waves, which move through the atmosphere. They move through space as well, and space is technically not a vacuum because there are things in the emptiness of space. And we know that waves can be described by sine or cosine functions, which we're really going to focus on later on. So first of all, the type of wave we're going to look at just now are called travelling waves or progressive waves. And I googled this definition, and it's simply that these are waves in which the positions of maximum and minimum amplitude travel through the medium. Hence, it's called a travelling or a progressive wave. Now, progressive in this sense means it moves from one thing to another. And remember, I said to you that with advanced higher, definitions are really important because we want you to use the correct technical language. So what I really want you to do is try and remember this definition and try and remember it in terms of it's a wave in which the positions of maximum and minimum amplitude travel through the medium, because that's the type of language we're expecting you to use. And as I said to you before, examples of these waves are sound, water, and electromagnetic waves. And I have a wee animation to show you it's a moving wave or a travelling wave. So, first of all, let's introduce this quantity of a phase. And this is just simply a quantity that tells us where a wave is at time t equal to 0 and x equal to 0. So this defines where the starting point of a wave is. And for example, if we think about our simple harmonic motion, we had y is equal to a sine omega t. So in this case here, the phase is actually 0 because it's starting at time 0 and x0. And if you draw the sine graph, you would have something like this. So we could put a plus 0 at the back there, and that would be your sine graph. So this would be telling you it's starting at the origin of the graph there. So that's where we talk about phase. Now, in fact, we're going to be focusing on phase difference because that really is where we get more interesting examples. So a wee bit of revision from higher. You may remember from higher that in phase was defined as where a crest meets a crest or a trough meets a trough, or if a wave is one wavelength out of step. So if we drew this diagram, then this is our first wave, this is our second wave, and they're in phase if the crest lines up with the crest and the trough lines up with the trough. So that was how we defined in phase. And if we moved one of these waves exactly one wavelength along, we'd say they were still in phase. Out of phase was kind of the opposite. This is where a crest meets a trough, or if they are half a wavelength out of step. So for example, here we've got our two waves, and you can see there the crest matches up with the trough matches up with the crest, so these are out of step. Or the other way we could look at it is if we move this wave, if these waves are slightly half a wavelength out from each other, so that's why they are out of phase. And we will be using this idea quite a lot, so it's worth revising this for future reference. Now, a slightly new concept is the phase difference. Now, the phase difference is noted by the symbol phi, so that's the Greek letter phi down at the bottom here. And it's a quantity that tells us the separation in position between 2 points on a wave as a fraction of that wave. So we're going to look at a more kind of numerical example in a minute, but this is a diagram to show you the wave. And supposing we've got a point P on the wave, or a particle P on the wave, and a particle Q on the wave, then there is a phase difference between these 2 points on the wave, or these 2 particles on the wave. And quite often we talk about 2 or more waves having a phase difference, and that's where it's usually a little bit more easier to imagine it. So let's look at the equation for a phase difference. So first of all, if we go back to a diagram, we can see we've got 2 positions P and Q, and we know the wavelength of the wave is just lambda. So that's a notation you've come across before. But the distance between P and Q, and this is a linear distance, so I'm not following the shape of the curve, I'm just following the straightforward displacement. So that is just represented by the letter x. And if we put all of these together, you get 2 pi over x is equal to lambda. So wavelength is in meters, distance is the x between P and Q, which is in meters, and phi is the phase difference. Now, oddly, although usually we use meters for wavelength and distances, you will find in some of the later examples next time that we will use centimeters as well. And part of the reason for that is because a lot of these waves we deal with are actually quite small. So just to summarize that, phase difference phi is equal to 2 pi x over lambda, and phi is in radians. Okay, now you might ask, where does this term 2 pi come from? And to be honest with you, I can't tell you it from this perspective, but if you look at your notes there, it does go into a little bit more detail about why you have a 2 pi. Part of it is because we are dealing with sine waves here, and we're going to talk about frequencies, so 2 pi's do come in into this, and that makes it easier to simplify these things. So how do we apply what we've learnt in advanced higher to our higher knowledge? So remember I said to you that at advanced higher, we're really looking at detail. So in higher, we talked about in phase as being crest to crest, trough to trough, or one wavelength out of step. At advanced higher, I would really expect you at the least to tell me it's one wavelength out of step. If you say crest meets a crest, trough meets a trough, it's not really rigorous enough. So the more advanced higher answer would be the following. It's when the phase difference is 0 for waves that are one wavelength out. And you can probably see why, because remember the phase difference is the difference between 2 waves. So if the difference between 2 waves is 0, that means they must have started exactly at the same point, or they're exactly in step with each other. Is there another value of phi that we could also take to say something is in phase? Pause the video and have a wee think. So hopefully you said the other answer is 2 pi, because remember 2 pi is exactly one complete revolution of the sine or cosine wave, isn't it? So that would mean we're going to meet up exactly one wavelength out. Now, I've kind of cheated a little bit there because I've started talking about sine and cosine waves. So at the end of the lesson, once you've kind of seen the whole thing, try and go back and fill in the missing links that I've tried to kind of mention here. And you can see there our crest meeting up with crest, trough meeting up with trough. So out of phase, again, going back to our higher, we wouldn't really accept this anymore. Crest meets a trough. Half a wavelength at a step, that would kind of be okay. But what's the more formal definition of it? Well, can you think of it? If in phase was when phi was 0 or 2 pi, when do you think the waves would be out of phase? So did you get that it was pi? Because again, if you think about your sine and your cosine waves, if you shift them along by pi radians, then they will be exactly half a wavelength out of step. And you can see that in my diagram there. So those are how we tie in this idea of phase difference with what we learned in higher. Okay, final bit here, and this is a wee bit odd, and I'm really going to go into it more when we look at the worked examples, but essentially the energy of a wave is given by its amplitude squared times a constant. So E is equal to K times A squared, and it can be rewritten as the following. So if we know the energy and the amplitude of a wave at one point, then at a later point, we know the energy of the wave will be given by the second half of the equation. And just remember, these are squared here. Don't get confused by all the kind of ones and twos floating around. And as I said, I'll go into more detail about this when we look at some worked examples. Okay, so having done all the kind of concept of what a travelling wave is and talked about some definitions, let's try and dig into the mathematics of what a travelling wave is. So there's a wee simulation here on PhET, which I recommend you try. I may try and do a wee video later on, but for just now, it's really just to kind of let you play around with it. But essentially, if we think about a travelling wave, usually we talk about time and the amplitude. And we did that when we did simple harmonic motion. But the one thing we don't really think about on this graph here is that, remember, a travelling wave is moving, which means it has a position that is changing. So realistically speaking, our description or equation of a travelling wave must include a position represented by the letter x. We know that it's going to change with time, so there must be a t quantity in it. And we know that there's an amplitude which is given by the letter y, or the direction y. So this is a bit unusual because we're going to have a function or an equation that has three variables in it: x, y, and t. So far, we've usually only dealt with two variables, y and x. So let's see how this actually works out. So first of all, from sort of simple harmonic motion, if you like, we know that y is equal to a sine omega t. And this is a nice straightforward one because we know that a is the amplitude, omega is the angular frequency, and that y varies with respect to time. Okay. Now we can do a wee bit of a substitution because we can substitute omega for 2 pi f. So you can see where that 2 pi is started to come in our phase difference. And we rewrite that, we have this equation here. Y is equal to a sine 2 pi f times t, where a is the amplitude in meters, frequency is in hertz, and time is in seconds. Nothing new there, I don't think, because we've kind of seen this in simple harmonic motion. And this is represented by this graph here, which again, you've kind of seen in simple harmonic motion. So a lot of kind of revision here, a lot of kind of recapping of reusing concepts that you've come across before. So how do we think about the displacement of the wave? Because in our graph from the previous slide, we've got time and we've got y, and we're fairly happy with that. We're fairly comfortable with that. But how do we deal with this x bit here? Because say, for example, we've got a wave starting at time t equal to 0, but at x equal to x. So that means it's already moved along a little bit here. Okay, well, if we think back to maths, in maths, for sine theta shifted to the right by x, we'd write this as sine theta minus x. And so in our description of a travelling wave, we can kind of use the same trick. So to tie it all together, we can say the equation for a travelling wave is y is equal to sine a sine 2 pi ft. So we got this from previously. And then instead of saying it as x, we say it's phi, where phi is the phase difference 2 pi x over lambda. Because remember, that really is the definition of phi. It's how far along this is compared to a previous point, depending on the ratio of the distance travelled to the wavelength. So to tidy this up a wee bit, because we know the wavelength, or the wave rather, is moving along towards the right, we use a negative instead of a positive, which I know is very counterintuitive, but mathematically is a very good reason. And I would say ask your maths teacher, because I really can't remember how that works. And then you can see why we've got the 2 pi, because we can take these out as a common factor, and we get the final equation, which is y is equal to a sine 2 pi ft minus x over lambda. And this is the general equation for a travelling wave. And what's a really useful exercise would be if you compare this with a general equation for simple harmonic motion, you'll see that they're fairly similar. Okay, so just to summarise, for a travelling wave going towards the right, it's given by this equation here, which you have to know off by heart. And for a travelling wave going towards the left, it is simply the same equation, but with a plus instead of a minus. And what we'll do next time is we'll look at how do we use these equations in advanced higher physics and what are the type of problems that we need to solve.